of equilibrium constant. It is broadly divided into three categories. The first one is predicting extent of reaction. The second one is predicting the direction of the reaction. And the third one is calculating equilibrium concentrations. Predicting extent of reaction. The numerical value of the equilibrium constant for a reaction indicates the extent of the reaction, but it does not give any information about the rate at which the equilibrium is reached. The magnitude of Kc or Kp is directly proportional to the concentrations of products and inversely proportional to the concentration of reactant. If Kc is greater than 10 to the power 3, products predominate over reactant. That is, if Kc is very large, the reaction proceeds nearly to completion. For example, for the reaction H2 plus Cl2 reversible 2HCl at 300 Kelvin, Kc of the reaction is equals to 4 into 10 to the power 31. Since Kc is equals to concentration of HCl to the power 2 upon concentration of H2 multiplied by concentration of Cl2, which is equals to 4 into 10 to the power 31. This implies that concentration of HCl to the power 2 equals to concentration of H2 multiplied by concentration of Cl2 into 4 into 10 to the power 31. Therefore, concentration of HCl to the power 2 is hugely greater than concentration of H2 multiplied by concentration of Cl2. Conclusion. Thus, concentration of product, that is HCl, is more than reactant, that is H2 and Cl2 at equilibrium. Text. The numerical value of the equilibrium constant for a reaction indicates the extent of the reaction, but it does not give any information about the rate at which the equilibrium is reached. The magnitude of Kc or Kp is directly proportional to the concentration of products and inversely proportional to the concentration of the reactant. If Kc is less than 10 to the power minus 3, reactant predominate over products. That is, if Kc is very small, the reaction proceeds rarely. For example, for the reaction N2 plus O2 reversible 2NO at 298 Kelvin, Kc of the reaction is equals to 4.8 into 10 to the power minus 31. So, Kc equals to concentration of NO to the power 2 upon concentration of N2 multiplied by concentration of O2, which is equals to 4.8 into 10 to the power minus 31. This implies that concentration of NO to the power 2 upon 4.8 multiplied by 10 to the power 31 is equals to concentration of N2 multiplied by concentration of O2. This implies that concentration of NO to the power 2 is very less than concentration of N2 multiplied by concentration of O2. Conclusion. Thus, concentration of reactant, that is N2 and O2, is more than product, that is 2NO, at equilibrium. Predicting the direction of reaction. Reaction quotient Q is defined in the same way as the equilibrium constant Kc, except that the concentration in Qc are not necessary at equilibrium. For a general reaction, AA plus BB reversible Cc plus GD, Qc is equals to concentration of C to the power C multiplied by concentration of D to the power D upon concentration of A to the power A multiplied by concentration of B to the power B. If Qc is greater than Kc, the reaction will proceed in the direction of the reactant, that is reverse reaction. If Qc is less than Kc, the reaction will proceed in the direction of the products, that is forward reaction. If Qc equals to Kc, the reaction mixture is already at equilibrium. Text. Definition. Reaction quotient Q is defined in the same way as the equilibrium constant Kc, except that the concentrations in Qc are not necessary at equilibrium. Calculating equilibrium concentrations. Let us understand calculating equilibrium concentrations. Let us take an example. 3 mole of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at 380 Kelvin. Calculate composition of the mixture at equilibrium. Since Kc is equals to 1.8 and initial moles of PCl5 is equals to 3. Now moving on to the solution. Step 1 is write the balanced equation for the reaction PCl5 reversible PCl3 plus Cl2. Step 2. Under the balanced equation, make a table that lists for each substance involved in the reaction the initial concentration, the change in concentration on going to equilibrium, and the equilibrium concentrations. Since initial concentration of PCl5 is equals to 3 and that of PCl3 and Cl2 equals to 0, let X mole of PCl5 be dissociated. So, at equilibrium, concentration of PCl5 equals to 3 minus X. Fill the number of moles of PCl3 and Cl2 in terms of X. Fill the equilibrium equation. Since Kc equals to 1.8, this implies that 1.8 equals to x square upon 3 minus x. This implies that x square plus 1.8x minus 5.4. Calculate the value of x. Negative sign is ignored since concentration cannot be negative. Step 4. Calculate the equilibrium concentrations from the calculated value of x. Concentration of PCl5 equals to 3 minus x, which is equals to. Calculate the value of PCl5 at equilibrium. Step 5. Check your results by substituting them into the equilibrium equation. Calculate the value of PCl3 and Cl2 at equilibrium.